Brooke has planned an exciting day out, and everyone is anxious to know where they are heading. But she doesn't want to spoil the surprise, so she ties the others in blindfolds. As Lotus, Mark and Ian hustle into the back seat of a taxi, Brooke silently shows the driver their destination. They start heading west along 3rd Street, but when the GPS updates their location, it tells them to turn around. At the next roundabout, they make a U-turn and continue east. Let's pause here to consider the motion of the taxi through the roundabout. It starts with a velocity of 7 metres per second west. Halfway through the turn, it travels 7 metres per second north. After a total of 5.4 seconds, it finishes with a velocity of 7 metres per second east. Although the speed remains the same, the direction changes. Therefore, the taxi's velocity changes and it accelerates. It's time to consider a conceptual question. What is the direction of the taxi's instantaneous acceleration throughout the turn? Is it north, east, south, west, or something else? Pause here to think about your answer. To make it easier to answer this question, let's split the motion of the taxi into 2 parts, each taking 2.7 seconds. Next, we remember that the average acceleration is equal to the change in velocity divided by the time taken. The change in velocity is the difference between the final and initial velocity. In the first half of the turn, the initial velocity is 7 metres per second west, and the final velocity is 7 metres per second north. By subtracting these vectors, we get a change in velocity of 9.9 metres per second northeast. It takes the taxi 2.7 seconds to travel through this section, so its average acceleration is approximately 3.7 metres per second squared northeast. Now, you might be wondering, why is the direction northeast? If we think about it, the car needs to stop moving west, which is the same as speeding up in the east direction. It also needs to start moving north. This explains why the change in velocity and acceleration are both northeast. By applying the same procedure to the second half of the turn, we find that the taxi's change in velocity is 9.9 metres per second southeast, and its acceleration is 3.7 metres per second squared southeast. The direction is southeast because the taxi needs to stop moving north and start moving east. Overall, we notice that the average acceleration of the taxi changes throughout the turn. However, our goal is to find the direction of the instantaneous acceleration. This might be different to the average acceleration because an average is not always accurate. To get a more accurate answer, we need to break the turn into many small parts. As we increase the number of parts and decrease the time interval, the average acceleration gets closer to the true value for the instantaneous acceleration. The correct answer is that the taxi accelerates towards the centre of the roundabout. Now, let's draw a free body diagram for the taxi. In the vertical direction, the weight force pulls the taxi down, and normal forces from the road push it up. The taxi doesn't move up or down, so these forces are balanced, and there is no net force in the vertical direction. Meanwhile, a driving force pushes the taxi forwards, but air resistance and friction push it backwards. Since the taxi travels at a constant speed of 7 metres per second, these forces are balanced, and there is no net force in the forwards direction. Earlier, we established that the car accelerates towards the centre of the roundabout. From Newton's second law of motion, We know that this acceleration is caused by a net external force. You might call this the turning force that is produced when the driver turns the steering wheel, but it's ultimately caused by friction from the road. To summarise, friction creates a net force that pushes the taxi towards the centre of the roundabout and makes it travel in a semicircle. This brings us to the centripetal force. This is a net external force that is perpendicular to an object's velocity. It makes things travel in a curved path.